All right. Hello, everyone. Welcome to our CS Development Seminar. Today is my great pleasure to have Professor Rene Vidal from Johns Hopkins University to visit us virtually and speak in our seminar. So Professor Vidal is the Herscher Seder Professor of Biomedical Engineering and the inaugural director of the Mathematical Institute for Data Science at Johns Hopkins University. He has a secondary appointments in computer science, electrical computer engineering, and mechanical engineering. He is also a faculty member in the Center for Imaging Science, the Institute for Computational Medicine, and the Library for Computational Sensing and Robotics. So Professor Vidal's research focuses on the development of theory and algorithms for the analysis of complex high-dimensional data sets, including images, videos, time series, and biomedical data. His current major research focus is understanding the mathematical foundations of deep learning and its application in computer vision and biomedical data science. So I think Professor Vidal is also leading a big team study the foundation of deep learning, which is funded by the National Science Foundation. And his lab has pioneered many development of method for dimensionality reduction and clustering. He is famous for his work in generalized principal component analysis and sparse subspace clustering. So when I was a graduate student, I remember I read a lot of his papers in dimension reduction and clustering, which is very like milestone works in the field. Okay, so please join me in welcome Professor Rene Vidal to speak. Okay, Rene, yeah, the stage is yours.
Thank you, Quang. It's a really great pleasure to be here. Thank you for inviting me and for such a kind introduction. I'd love to be there. I've been to UCLA many times. In fact, I visited Stefano Soato when I was a PhD student at Berkeley, and I stayed at UCLA for one semester. So I have very fond memories of really fantastic campus and faculty and students. So thank you for having me. So, as Quang was saying, I became the director of the Mathematical Institute for Data Science at Hopkins that was just created a couple of years ago. And it brings together faculty from many departments and schools at Johns Hopkins who are broadly working on the mathematical, statistical, and computational foundations of data science. The Institute has been growing a lot, and we have on the order of 30-something faculty right now, but primarily we were given a number of faculty positions. So we recruited one faculty each year for the last 2 years, and we are recruiting this year as well. The university also has received, I think, more than 50 endowed chairs from Bloomberg, who was a student in electrical engineering at Hopkins. And so there will be a new recruitment season for 50 more starting the coming year. So if you have great students and faculty interested in joining, please get in touch with me. So in terms of the Institute itself, I think Quang was asking me what are the major sources of funding and research. So one is this NSF Tripods Institute. So that brings together a subset of the faculty, and the focus really is on what I tend to call AI 3.0. I see AI 1.0 as having focused on the models, mathematical models, statistical models, general graphical models, and I see AI 2.0 as being focused on deep learning. So the future is really going to be the integration. Do we need to learn everything, or do we? Probably not. Can we model everything? Probably not. And so the right integration of the two. And we've decided to focus particularly at the integration of graphical models and deep learning for the moment. And in addition, as part of this institute, we are doing a lot of activities for training and education, including seminars, symposiums, summer schools, and so on and so forth. The other main initiative of the Institute at the moment is this large NSF-Simons collaboration on the mathematical and scientific foundations of deep learning. This is a consortium that involves not only Hopkins, but also Berkeley, Duke, Penn, Stanford, and LMU in Germany. And really the focus really is, of course, in the foundations of deep learning, but in particular trying to understand a variety of properties, like why is it the case that they transfer so well to so many tasks? What about the expressivity properties, optimality? Can we ensure that deep networks make robust and safe and fair predictions? Can we ensure that the predictions they make are interpretable? So how do we understand the mathematical and statistical foundations of all of those aspects is the main theme behind this team. And myself, I'm really, I work in many of the aspects of the mathematics of deep learning. I have a lot of work recently, not published yet, on robustness of deep networks. But what I'll be talking about today is really more focused on optimization. And the reason is that optimization has really become mainstream in machine learning. It's kind of really interesting that optimization has existed for a very long time, and we began in the 50s with very simple first order methods. They became more and more sophisticated, but now with deep networks, we've gone back to first order methods again in stochastic optimization. So today there is a rich variety of methods being applied to very, very large scale non-convex optimization problems. And even though optimization has a rich history, there are still many, many open questions. And usually when I give a tutorial, and in previous times that I've been at UCLA, I have spoken about the math of deep learning in detail and many of the aspects. But today, my focus is going to be a little bit more narrow with just two main aspects. The first one is one aspect of optimization, which is the question of acceleration. Is it possible to build optimization algorithms with faster convergence properties? And what are the principles that allow one to do so? And can we come up with maybe new algorithms that are guaranteed to be faster, and how? And the answer is going to be really the interaction between optimization and dynamical systems. And I'll focus at least 2 out of 3 parts of the talk today on that topic. And towards the end, I will give a brief, small summary of some results that we've developed in the last 5 years pertaining deep networks in particular, and certain classes of non-convex problems, where the study is more on the aspects that pertain to the landscape and trying to understand whether one can have guarantees of global optimality and convergence for those non-convex problems. But the first part is primarily going to focus in convex optimization. So let me begin then with the first out of the 3 parts of the talk that is going to go from optimizations to dynamical systems. And what do I mean by that specifically? We'll begin with an optimization problem. We are going to look into some optimization algorithm, say gradient descent. And we are going to take some process that is called continuous limit that typically arises by setting the learning rate to 0. And when we do so, we're going to get some continuous dynamical system. And the question is going to be whether we can use those continuous dynamical systems as an analysis tool. And in particular, can we explain convergence, or can we explain the acceleration properties of the optimization method by analyzing the continuous counterpart? In the second part of the talk, I'll go backwards. I'll begin with some continuous dynamical system. In particular, we'll focus on Hamiltonians, and we'll discretize them. And the discretization is going to lead to new optimization algorithms. In particular, I'm going to be describing a new method we just developed called relativistic gradient descent that has very nice theoretical properties and emerges as the discretization of a particular type of continuous dynamical systems. So with that introduction, let me introduce some notation and begin to get into some of the details of what I'm going to talk about. So let's begin with the basic notation. Suppose that we have to minimize some function f of x, and this is just unconstrained optimization. So let's consider now one optimization method, which is in this case gradient descent, where the new value of x is equal to the current value of x minus some eta, which is the learning rate or the step size, times the gradient of the function. And so the idea of this continuous limit, as I said earlier, is what if this eta, this learning rate, goes to 0? And as you can almost imagine here, if I just take the difference xk plus 1 minus xk, the difference between two consecutive iterates, and divide by the step size, then I'm going to get the derivative on the left-hand side. And that's exactly what this continuous limit is about, that I have the derivative of some continuous variable now, and on the right-hand side, I just get minus the gradient. And so that's how I go from an optimization method to a continuous differential equation. And this first order optimization method now is transformed into a first order differential equation. And so now you can begin asking questions is like, say if f is a convex function and I can have a guaranteed convergence of gradient descent, at what rate? And now I can look at the differential equation and I can ask, do they converge and at what rate? And so the answer is yes. And this is the convergence rate of gradient descent for discrete functions is like 1 over k, where k is the iteration. And in continuous time is like 1 over t. And a very interesting property that is observed here is that the rates match, namely it is 1 over k in discrete time and is 1 over t in continuous time. I saw someone raising their hand, so there is a question maybe.
Yeah, I just had a quick question. Can you explain again how you converted gradient descent into a continuous problem?
Let me see if there is any way that I can annotate. It does not seem that annotation is enabled in Zoom.
Yeah, for this Zoom webinar, we don't enable that function. So sorry about that.
Okay. So let me try to.
But we can see your cursor. So if you move your cursor, we can see it. Yes.
Yes. So for some reason, I cannot go back anymore. Give me 1 second, please. Oh, well, it seems my computer is stuck now. Let me stop the sharing and restart, okay?
Sure, take your time, no worry. Yeah.
Okay. Okay. Can you see the big screen again?
Yes, we can.
Okay, good, great. Okay, so let me re-explain that. So if I take the difference between xk plus 1 minus xk, that is sort of a discrete gradient, if you wish. But then the derivative, the definition of derivative is the value at t plus 1 minus the value of t divided by delta t. And when you take delta t going to 0, that's when you get the derivative. So the difference between xk plus 1 minus xk and divided by the step size, if I let now the step size go to 0, that is how I get the derivative. Does that answer the question?
Yeah, thank you very much.
Thank you. Thank you for your question. Okay, so what is interesting then is that you might now ask the question, well, maybe analyzing the discrete algorithms is difficult, but maybe analyzing the continuous algorithm is easier. And now if they do have matching rates, then I could do all of the analysis in continuous time and then try to extrapolate the conclusions to discrete time. And so that's sort of the long-term goal. In 1983, Nesterov proposed a variant of gradient descent, which is what you see here. And this variant of gradient descent looks pretty much like gradient descent. The new x is equal to the previous x minus eta times the gradient. But the only difference really is that it's not the previous x, it's the previous x hat. And this x hat is a new variable that is also updated. And the new x hat is equal to the previous x plus this sort of derivative. This is sort of what is called momentum, or the difference between two consecutive variables. So it's sort of a velocity term, if you wish. And what was very mysterious is that with this one extra variable and one extra line of code that didn't change too much, you could get a convergence rate that instead of being 1 over k is 1 over k squared. And that's exactly the phenomenon known as acceleration. And that's why this method is called accelerated, Nesterov accelerated gradient descent. So this was a remarkable result, and it's been used quite heavily as an optimization method. But the understanding of why this modification leads to acceleration remained very mysterious for quite some time. And so it was not until this paper by Candace, Boyd, and Su in 2016 that they did this continuous limit again. And they showed that you get a second order differential equation, which is illustrated here. The R parameter is exactly the R that is there. It's typically chosen to be 3, in fact, for this method. It's 1 over t, so it's time varying. And again, the gradient shows up on the right. And now you get this second order differential equation. And the analysis of this second order differential equation is actually easier in continuous time. You can use standard tools from dynamical systems like Lyapunov functions or stability theory. And you can show, in fact, and that's what they showed, sorry, that you get a rate of 1 over t squared, which is exactly the rate that Nesterov had derived in continuous time. And that led to a lot of work following up, a lot of it being done by Michael Jordan and many of his students, where they extended this in many directions. So the analysis was done for smooth functions and primarily using these either first order or second order gradient-based methods. So what I'm going to be talking about today very briefly is the work of Guy Franca, who was a postdoc in my lab, and he's now with Michael Jordan at Berkeley, where he has extended this in many directions. The very first one is, what about constraint optimization problems? And in particular, one well-known algorithm for constraint optimization is accelerated alternating direction method of multipliers, or ADMM. And so what he did was to derive both continuous limits of both the classical ADMM as well as the accelerated version, as well as convergence rates. The second one is, what if I cannot take derivatives and I am facing non-smooth optimization problems? Can this be, can we extend methods like proximal gradients to continuous time? Can we extend splitting methods to continuous time? I'll just mention this very briefly, the key results, but won't be able to get into details. And last, and this I will spend a good 15 minutes, and this will be one of the main topics of the talk, is this relativistic gradient descent method, where we go backwards. We begin with a dynamical system and we discretize it, and we obtain new optimization methods. Okay, so let me begin with the first topic very briefly. What about constraint optimization? So suppose now that instead of just having to minimize f of x, I needed to minimize the sum of two functions, f of x and g of z. And suppose that these two variables were linearly related. So here, z variable is A is a matrix and it's a linear transformation of x. This style of problems show up a lot in many applications, particularly in imaging and in computer vision. Typically, X might be an image I want to reconstruct, A might be a Fourier basis or an MRI, for example, and Z might be the observations. And typically you have a loss function and a regularizer. So this is a classical problem. Or L1 minimization is another example where this is done. And so what we've been able to show is that if you take the ADMM algorithm, which is a primal dual method, where you update X, you update Z, and you update Lagrange multipliers, you can eliminate actually all variables and arrive at a differential equation in only one of them, which is X. And the form of this differential equation is pretty much like gradient flow. Gradient flow, if you remember, was just X dot is equals to minus the gradient of the objective. And the main modification is that you have this A transpose A on the left. Okay. By analogy, you can also do this for an accelerated version of ADMM, where you accelerate it in the same way that you do it for the Nesterov case. And what you get in this particular case is, as before, a second order differential equation. And it is the same that you would have gotten that Boyd and Candice and Sue derived, except that on the left you have the multiplication by A transpose A, which is what defines the constraint. Now, what we've done is not just to derive what the continuous limits are, but we also focused on the question of stability. Is it the case that if I evolve this differential equation, I will converge, and for what classes of functions and under what conditions? And again, using tools from Lyapunov stability theory, you can show that this differential equation will converge and will converge to the minimizer of that objective. So that's one theoretical result. Similarly, you can show the same thing for the accelerated ADMM flow. But even more, you can also derive convergence rates. So for ADMM in continuous time, we've been able to derive that the convergence rate for convex problems is 1/t. And for the accelerated version, which is this differential equation here, is 1/t squared. Okay. So the next part of Guy's work is the extension of these results to non-smooth problems. So, everything I've said so far, F was assumed to be convex and differentiable. G was assumed to be convex and differentiable. So what if they are not convex or differentiable? So in that case, the same style like we had a differential equation before, but now the gradient is not defined. So we cannot have something like X dot is equal to something. So what we have instead is that we can compute what is known as the subdifferential of the objective in the far right. And the subdifferential is not unique. Is a set. And therefore, what we have is what is known as a differential inclusion, which simply means that X dot belongs to that set. And so now the analysis is really significantly more complex on the dynamical systems, and you have to do this non-smooth analysis, Clark subdifferentials and whatnot in theory. In practice, what we were able to show is that for whenever F and G are convex, you can still connect these to splitting methods. And so that's part of the results we have today. But anyhow, we also did the analysis for the accelerated version, and again, you get differential inclusions. And despite the non-smoothness, we were still able to show that you get the matching convergence rates. So 1/t for ADMM and 1/t squared for the accelerated version. And if you care to know the rates with a lot more detail than I've talked so far, for example, for ADMM, if the function is convex, is not just 1/t, there is a constant, and that constant in this case is the largest singular value of the A matrix that defines the constraint. In the strongly convex case, instead of 1/t, we were able to show that you get exponential convergence. So it's e to the minus mu t, mu would be the constant of strong convexity, Kappa of A here would be the condition number of the matrix A. And sigma 1, as before, would be the largest singular value of A. And I don't want to get into the details, but I think this shows sort of a summary of all of the contributions of this first paper of Guy, where he derived the convergence rates for ADMM, accelerated ADMM, and many variants, like this last one is the heavy ball algorithm as well. All right, so to summarize this first part, I think the key message is that acceleration, namely going from 1 over k to 1 over k squared in convergence, can be explained via continuous dynamical systems. And the analysis applies not only to smooth functions, but also to non-smooth and to constraint optimization problems. And that one can derive convergence rates for a variety of different function classes, including convex and strictly convex problems. And the interesting observation is that the continuous and the discrete rates match. All right, so let me now move to the second part. So in the first part, what I did was begin with an optimization problem, take continuous limits, and then analyze the resulting continuous dynamical system. What I want to do now is to go backwards. So we're going to begin with a continuous dynamical system. We're going to discretize it, and that will lead to optimization algorithms. And the question is, and what is very interesting is that many of the well-known existing optimization methods can actually be derived as discretizations of dynamical systems. Specifically, what is the framework? The framework is to begin with what is known as a Hamiltonian. If you ever took a class in physics, and I barely remember because I took it probably 25 years ago. In physics, you have this quantity called kinetic energy, and you also have a potential energy. And what is the connection with optimization? The connection at a very intuitive level is that if you have a particle and the particle moves, they try to minimize the potential energy. And so the connection here is that we are going to let the function that we need to optimize be the potential energy of this Hamiltonian. And then we have the kinetic energy, and that's what the T of P is. So Q denotes the position of the particle, and it's going to be our optimization variable. P denotes the momentum, and as I said, H denotes the Hamiltonian. And the equations of motion of a Hamiltonian system are well known, and they're here on the right. So the velocity, Q dot, is just the gradient of the Hamiltonian with respect to P, which is the momentum. And the derivative of the momentum is minus the gradient of the Hamiltonian with respect to Q. Okay, and it's only the part in blue. And maybe the thing you might remember from physics is that energy is preserved. And this is exactly what these Hamiltonian systems capture. Okay, so these are energy preserving systems, and typically the sum of the kinetic energy and of the potential energy is a constant, even though the particle might be moving. So what we're going to do here, though, is to consider a class of Hamiltonians that have dissipation, and those are called conformal. And the dissipation is this additional red term here that is minus gamma p. At an intuitive level, why do we want to add dissipation? Well, if there is no dissipation, imagine a pendulum that is just moving, it'll never converge. We want to do optimization, and we want our iterates to converge to the global minimum. So we are going to add dissipation, which is equivalent to having this pendulum move back and forth and eventually converge to the equilibrium point. And so the minus gamma rate, ideally, we would like it to control the convergence rate. Okay, so let's derive an optimization method then. So again, let me repeat, the f is the function that we want to minimize. And I postulate that if we write down this differential equation, then it will converge to point Q, that is the minimum of f of Q. Okay. And so what we're going to do is now take this differential equation that is on the right, and we're going to discretize it. And the discretization goes backwards. So instead of having q dot, we're going to write qk plus 1 minus qk divided by eta, approximately. It's a little bit more sophisticated than that. Now, in doing so, in order to guarantee this convergence, we would like to have the property that the volume is shrinking as a function of time. And mathematically, this is captured with what is known as the volume form. It's called symplectic 2 form in symplectic geometry. And a particular property that this volume form has for these Hamiltonians is that it goes down to 0 exponentially fast. So if W0 were to denote the initial volume, then the volume at time t is e to the minus gamma t times the initial volume. In a Hamiltonian system without dissipation, that volume is constant. Okay? But in this, the addition of dissipation is exactly what's going to allow us to contract. So when we discretize, we are going to have a new q and a new p at every iteration. And we would like to have something like this. And this is what's going to allow us to connect continuous rates like e to the minus gamma t here with discrete rates. And this is a definition. So a numerical map, so an integrator or a discretization of this differential equation, denoted here by qk, is said to be conformal symplectic if it shrinks the volume form in the same way. So this is the volume form at iteration k plus 1. This is the volume form at iteration k. And notice that there is e to the minus gamma h, and h is going to denote the step size of my discretization. Okay. And if that's the case, in discrete time, we're going to have this same contraction. And that's what's going to ensure the convergence with a rate that will depend on gamma. Okay, so that's very high level at this point. And I'm going to provide a concrete example in the next slide, but let me just repeat at a high level to make sure it's clear. We're going to begin with a Hamiltonian. We're going to let the potential energy be the function that I want to minimize. We're going to look at the differential equation on the right. We'll discretize it, and magic is going to happen. Specifically.
So can I have a question?
Yes,
about
of course.
Yeah. So here H is the, if I understand it correctly, is H the step size you are going to use to do the discretization?
Little h, and I apologize.
Yeah, little h. Yeah.
I apologize for the abuse of the notation. So capital H is the Hamiltonian, little h is the step size of the discretization.
I see. And this dq, for example, dqk plus 1, should I understand it as qk plus 1 minus qk, or it is qk plus 1 minus qk divided by h? So what's the definition of this dqk plus 1?
Yes, it's going to be the qk plus 1 minus qk.
Okay. Thank you.
Yeah. Okay, so let me give a concrete example. And so in this concrete example, I'm going to choose the kinetic energy to be the kinetic energy that we learn in physics. You may have learned it as the mass times the velocity squared divided by 2. In this case, it's expressed in terms of the momentum. So it's the momentum squared divided by 2 times the mass of the particle. So that's what this term is. And the second one is the potential energy that, as I said, is my function. So in this particular case, the dynamics are linear for Q and almost linear for P. The only nonlinear part is minus the gradient. And in this case, you can now discretize. So here is a particular discretization. So the discretization at the bottom should be relatively straightforward. Is the new Q is equal to the previous Q plus the step size times the derivative. And so the derivative is here on the right-hand side. So it's exactly P divided by M. P divided by M, this is exactly what shows up here. Okay. The integration of this one is a little bit more involved, but let me just leave it there. Again, h becomes the size of the discretization, so it becomes analogous to the learning rate. And okay, so for now, you know, this just looks like as if I was talking about dynamical systems, and h is the step size. I discretize a gamma. If you do a tiny change of variables, like if the mass you substitute it by h and you let mu be e to the minus gamma h, you get exactly a well-known optimization method known as classical momentum algorithm. And so the first and immediate observation that happens here is that you can obtain the classical momentum method by discretizing a Hamiltonian with dissipation, okay? And that's the first part. The second part is that you remember, and Quan, you asked me a question about this preserving the volume or letting the volume shrink exponentially. It can be proven that this discretization has that property of shrinking the volume exponentially. And that property, being conformal symplectic, shrinking the volume, is critical to have these matching rates between continuous and discrete time. And that's exactly what this first theorem says, that the classical momentum method not only emerges as the discretization of a Hamiltonian, but it's actually conformal symplectic integrator of the Hamiltonian, which means that this volume shrinkage property is preserved, and that allows you to connect, even though I'm not discussing that, that's a recent paper, the discrete time rates with the continuous time rate. So in the past, people just observed in parallel that the continuous rate matched the discrete rate. What this property of being conformal symplectic allows us to do is to connect the two. Namely, we can derive the rate in continuous time and then use the connection between continuous and discrete via the conformal symplectic property to derive the same rate in discrete time. Next, you can now begin looking at different optimization methods. And you can now write down Nesterov acceleration method as I've written here. And now you can try to check that property that I was talking about, the conformal symplectic. And in this case, is not satisfied. So that establishes a key difference between classical momentum and Nesterov acceleration, that one of them is a conformal symplectic integrator and therefore shrinks the volume. The other one is not. That does not imply that it will not converge or will not have nice properties. In fact, we already know that Nesterov has very nice properties, but at least they cannot, the link between continuous and discrete cannot be derived via the theory that we've developed. Let me move next. You know, insofar, what did I do? All I said was take a Hamiltonian, discretize it, and if the energy is the classical kinetic energy, you will get the classical momentum method. But the choice of the kinetic energy is arbitrary. I can choose any kinetic energy that I want, and maybe different choices of kinetic energies will lead to different optimization methods. And so one such choice is the relativistic energy, which is defined here. So C denotes the speed of light. P squared is, as before, is the momentum squared. MC is the mass times the speed of light squared. And so that's the new kinetic energy. And on the right is the potential energy, that is the function I'm trying to optimize. These are the same equations as before. This is the same Hamiltonian. It's just substituting the kinetic energy, taking the gradient of it with respect to P, and that I get what's here on the right. And now we're going to play the same game. I'm going to take this differential equation and discretize it. And this is what I get. I get a new optimization method that didn't exist before. And this new optimization method looks very much like momentum method, but there is now a normalization that is happening here. Okay. And if the mass or the speed of light is very, very large, if I let them go to infinity so that I can neglect this term, right, then I'm going to get P divided by MC, and that's going to reduce to the classical momentum method that I had before. But otherwise, this is leading to a new optimization method that induces normalization. We've not understood it fully yet. And so in fact, a lot of the future research is to understand properties of this method. Does it converge? Does it not? When does it converge and when not? And particularly, we believe that there could be connections with Adam, which is also another method that is based on normalization. And generally, it is believed that by suitably normalizing some of these gradient methods, one can get better acceleration and better convergence properties. But as I said, we've not done the theoretical analysis yet. But we have done a lot of experiments, at least for simple problems and for some that are very more non-convex. And so let me show you a few synthetic examples first, and then I'll show you a little bit the performance of it in some simple types of deep networks. So to begin with, this is just in theory a simple problem because it's just a problem in two variables, but it's one that is actually very complex in the sense that it has many local minima, and that is very hard to converge to them. And so it's typically used as a function on which to test some of the complex optimization methods. So what you see here is plots. The y-axis is always the value of the function. The x-axis is the iterations of different optimization methods. And the plot on the left is just with one initialization. The plot on the right is with a different initialization. Three methods are being compared. One of them is classical momentum in blue. The other one is Nesterov accelerated gradient. And in red is this relativistic gradient descent. And I hope that, you know, the problem is non-convex, but I hope you appreciate that there is a significant improvement in the speed of convergence for these non-convex problems. And this is true for different initializations. In the paper, you can find lots of different initializations, different rates, and sort of the variance of performance. And these averages that I'm showing here are representative of the behavior for this specific function. This is another toy problem that is also very complex, and it's sort of illustrating the same behavior, where the red, which is the relativistic gradient descent, tends to converge much faster than some of the state-of-the-art competing methods, such as classical momentum and Nesterov accelerated gradient. Getting a little closer to a real problem. This is the problem of matrix completion that is fairly commonly used for recommendation systems. Movie recommendations, the Netflix challenge is another such problem. In this type of problems, you're given some matrix M. That matrix M could be, for example, the ratings of the movies from Netflix. So it could be number of users times number of movies, and each entry will just be a rating for that movie. And because users tend to rate very few movies, that matrix is largely incomplete. And so omega here is the set of observed entries, and omega complement is all of the movies that users have not rated. So the goal is to complete or to predict the ratings for other movies, or try to predict what are the preferences of the users. And the approach is that you exploit the fact that that matrix is low rank. The reason for it being low rank is maybe because there is a few number of genres of movies. And so A times B here denotes that low rank factorization. And in order to induce that this matrix be low rank, typically you use regularization. And in this particular case is the norm of A squared plus the norm of B squared. It is the Frobenius norm, and so what's on the right is a standard regularizer. So now let's say you just run any optimization method. Here you can run gradient descent on A and B. You can run Nesterov accelerated gradient. You can use relativistic gradient descent here in green, or a well-known and well-studied soft input alternating linearization method for specifically designed for matrix completion. So on the left, as before, what we have in the y-axis now is the completion error, and on the x-axis the time instead of the iterations. And this is two different movie data sets, the movie lens UA and the movie lens UB. And the main observation is, well, gradient descent is the slowest method, that's in blue. But then I guess you see between green and red, so Nesterov accelerated gradient and red is the soft input. And so the green method is the relativistic gradient descent. So initially it's a little bit slower than soft input, which is specifically designed for the problem, but as time proceeds, it gets to be the fastest method. Okay, so this ends the second part of the talk. And really the union of everything I've said so far is that we can go from optimization to take the continuous limit and do better analysis and get matching rates. Or we can begin with a continuous dynamical system, a Hamiltonian, and discretize it and derive new optimization methods like this relativistic gradient descent that seems to be better than state-of-the-art methods, but still we have not developed the theory for it. Let me move now in the third part to the analysis of landscape, not optimization methods, for deep networks. And for, actually, this is true for a variety of different non-convex problems. So these are the kinds of questions in non-convex optimization. So what is the error surface like? Are there many global minimizers? Are they all isolated? Are there many local minima? Or there could be here a global minimum that is not isolated. Or here there is a local minima. What is the landscape like for, say, matrix factorization, tensor factorization, or deep networks? Can we have guarantees of finding the global minimum? When is it the case that a local descent strategy may succeed in finding the global minimum? For what classes of architectures? For what classes of nonlinearities? So usually I give a full hour talk on this, so I'll just be very brief here and sort of state the results at a very high level, but happy to answer more questions if there are. So what our work, and this is really the work of Ben Haefele, his PhD thesis, he asked the following question: are there properties of the network architecture that make optimization easier? And the answer was that there is this property known as positive homogeneity that makes optimization easier. In particular, many well-known and well-used nonlinearities, such as rectified linear units, are positively homogeneous. Max pooling is positively homogeneous. Many of the commonly used pooling operations are as well. So typically, therefore, the interaction of linear layers with homogeneous nonlinearities will lead to homogeneous networks. And typically, though not always the case, you will have that every layer of the network will increase the degree of homogeneity by 1. And so typically, you will have that a network with k layers will have degree of homogeneity k. The second property of the architecture that was identified to be good for optimization is the idea of parallel subnetwork structure. What is meant by that is that you need to increase the width of the network. You can do so by adding more neurons to say a single hidden layer neural network, or you can do that by putting many subnetworks in parallel and then adding them up. Right, so that's going to be sort of the assumptions of our theorems. So we're going to assume, therefore, that networks have this parallel structure and that the input-output map of every subnetwork is positively homogeneous. The second aspect of the framework is to add regularization. So classical regularization is to do weight decay, sum of the square of the weights. Here, we are going to do something like that, but we are going to require that regularizer to be positively homogeneous as well. So weight decay, sum of the square of the weights, is of degree 2. And a key property that we will require of the regularizers is that the degree of homogeneity needs to match the degree of homogeneity of the network. So networks with k layers would typically be of degree k, and so we will need regularizers of degree k. And last but not least, and this is the last point here, is that we need to adapt the network structure. So our theorems don't apply to fixed networks, but rather to networks where, as you are optimizing, you might add more neurons and make them typically wider and wider. And the role of the regularizer is to penalize making the network too wide. And in that way, therefore, the structure of the network is adapted to the data. And so the richer the data, maybe the more neurons that I need to put in parallel, or the more subnetworks I need to put in parallel. So with that very high level description of our assumptions, let me just have some high level description of the kinds of theorems that we are able to show. So as I said, the idea is that we're going to have these networks that have many subnetworks in parallel. And the type of theorem that Ben was able to prove is of the following nature. As I said, if the network has parallel structure, is homogeneous of, say, degree k, and the regularizer is also homogeneous of degree k, then if you're able to find a local minimum for the network such that all of the weights of one subnetwork are 0, essentially sort of suggesting that that subnetwork is redundant and that I've made it too wide. That condition, namely a local minimum with 0 weights, that's a guarantee for that local minimum to be global. Okay. And to illustrate in pictures why we can get results of global optimality for deep networks, even though they're non-convex, the key idea really is the following. The landscape for the deep network might be the blue one. So the blue one is the loss plus the regularizer as a function of the network weights, W. And so what we've shown really is the existence of a convex function that is a lower bound. And it's a convex function not on the weights, but rather a convex function on the output of the network. And therefore, even though the problem is non-convex on the network weights, there always exists a convex problem on the output of the network. And the global minima agree, as illustrated in this figure. So namely that if I have a global minimum for W, I can always find the global minimum input-output network. Or conversely, if I find the minimum input-output network, I can always find the weights that match. Okay. And that's exactly what is said here, where the minimum of the loss with respect to all of the weights, the minimum value, is the same as you take the optimum weights, you pass them through the network to get the output, and that Z will also minimize the same loss function, but as a function of the output. The second theorem is that if the size of the network is sufficiently large, you can always find a global minimizer from any initialization by following a local descent strategy. What I mean by a local descent strategy, I don't mean gradient descent. Again, remember that the framework requires you to adapt the architecture as you move along. And so the idea is going to be that we will, for example, maybe let me illustrate it. I think I illustrated in the next, but the idea is that you will begin with a network here, go down, then choose that you need to increase the number of networks, and then repeat until you find the global minimum. Why is that possible? I mean, this was very mysterious the very first time. So eventually it took me a while to come up with this picture that illustrates really what's going on. So what I'm trying to advocate is that rather than optimizing over fixed architectures, in order to facilitate optimization, we need to make networks bigger. And why making networks bigger facilitates this? The idea is the following. Suppose that you only had an optimization problem over one variable, such as the one illustrated here. And it's obviously non-convex, and you can get stuck. And let's suppose that I got stuck here in this local minimum. What we're going to do is we're going to ask the following question. If I were to add, say, one more neuron, let's say it's a network with a single hidden layer, and I have 3 neurons in the middle layer, and I decide to add one more. When I add one more, I'm going to have new weights, right? So the picture here, what it's meant to illustrate is that I had only some variables in blue, but I added a new direction. So when I add that new direction, when I add that new neuron and the new weights, it could be the case that now in the new space that has both the old and the new weights, I can find the descent direction. And that's exactly what's illustrated here. So in other words, the local minimum in one variable here gets converted into a saddle point in 2 variables. And because of that conversion into a saddle, if I can find now a descent direction, I'll keep going down. At the other extreme, if I am at a global minimum, if I try to add one more variable and another dimension, because it is a global minimum, I will not be able to find a descent direction. And so that motivates exactly the algorithm or the meta algorithm that I was talking about, that let's say you begin with 1 neuron, you minimize, you get to a local minimum. You check, can I find the descent direction? Yes or no? If I cannot find the descent direction, that's because I found the global minimum. But if I can, then I add one more neuron and I keep repeating the process. And eventually I will stop. And our theorems state that you stop after a finite number of neurons that you add, or in the more general case of a deep network with many subnetworks with parallel substructure. The idea is that you keep adding subnetwork in parallel and eventually you stop after a finite number of subnetworks. So with those results on the landscape, we began doing now some experiments.
I have a quick question. So can you go back to previous? So so here you are talking about the spurious local minimum, so I don't see any like a spurious local minimum on this graph. So are you saying that this is actually a 3D visualization of some landscape, so that this wide curve is like another coordinate of the optimization variable?
So maybe the use of the word spurious is not entirely adequate. So maybe let me define what I meant by it here. A spurious local minima is a local minima that is not global.
Okay, I see.
And so what I'm saying here is that if you are at a local minimum that it is not global, then you can find the descent direction by adding another subnetwork in parallel. And that creates a saddle.
I see.
Yeah.
Okay, thank you.
Okay, so let me now conclude the talk with a few experiments on some simple, relatively simple neural networks. Where this is still preliminary results in the sense that we have the analysis of the landscape. We have the analysis of this relativistic gradient descent maybe for convex, or actually of the classical momentum algorithms for convex problems. And now we're trying to do experiments that put the two of them together and trying to get rates, but we don't have the theory and the results yet. So I'll just be showing experiments here. So this is the simplest case where we're training LeNet on the MNIST data set. The plot on the left shows the loss function during training, and the plot on the right shows the classification accuracy. Actually, I think this is being shown both training and testing. So I think the solid lines like this group is during training, right? So it's showing the training is working, is going to 10 to the -6 here. And the accuracy is going to essentially 100% during training. During testing is shown here, so the loss function sort of gets stuck, and the accuracy also gets stuck at a lower level, like 99%. This is because the LeNet is not the more complex network that achieves 99.99% in MNIST. It was just to illustrate the optimization method. So here, the surprise was that we didn't see major differences, as remember probably from the more synthetic experiments that I had shown before. We do see it during training. So you can see that relativistic gradient descent, that in this case is in red, that's better. Adam in particular is one of the methods that gets stuck. But there is not a major difference between relativistic gradient descent and classical momentum, which is in orange. Nesterov accelerated gradient is a little bit worse. And what you see, the shadows here denote just the variance across different trials. Okay, so for MNIST, not a major difference. This is another example now where we train a bigger network, ResNet 34, on the CFAR 100 dataset. On the left, you see the training loss. On the right, you see the validation loss. On the left, I think, again, not a major difference between classical momentum, Adam, another variant of Adam. And here what we did was two different versions of the relativistic gradient descent method. Remember that we take a Hamiltonian and then we discretize it. When you discretize it, you can choose various discretes. So the Euler method is the one that I pretty much talked about throughout the entire talk. But there are other methods like the leapfrog that it's a little bit more sophisticated. So not much of a difference during training, but you can see that if we just look at the validation loss, it's sort of clear that Adam and both variants of Adam are a little bit worse than classical momentum, and the two different variants of relativistic gradient descent get a lower loss during validation. We see a somewhat similar behavior in terms of the accuracy, classification accuracy. So again, Adam is the red and the brown here achieve a lower accuracy, while in this case classical momentum and both variants of relativistic gradient descent achieve a higher accuracy. This is during training, and you can see a similar behavior during testing, again with the two versions of relativistic gradient descent having a little bit of a better performance even than classical momentum. And this is just illustrated here at the bottom. It's sort of just repeating. What you see over there is all the trials and the variants. What you see here is sort of the average performance with the relativistic gradient descent with the leapfrog integrator method achieving the highest average performance. All right, so let me stop there. So to summarize, I think I try to convey two major points in this talk today. One is that there is a nice connection between dynamical systems and optimization, and that continuous dynamical systems are an excellent analysis tool for optimization methods. They can be used to explain acceleration. They can be used to derive convergence rates, and they can also be used to derive new algorithms like this relativistic gradient descent. And in the last part of the talk, I talk a little bit about landscape and particularly understanding classes of deep networks, such as those that are positively homogeneous and with parallel structure, that have a simpler, quote unquote, simpler landscape, in the sense that you can derive guarantees of global optimality. And a key insight is that you need to adapt the network size as you do optimization. So with that in mind, thank you very much, and I'm happy to take more questions.
Thank you for the great talk, Rene. So yeah, let's take more questions. Oh, we got a question from audience. Let me unmute. Okay.
Hear me?
Yeah, we can hear you.
Okay. May I ask a question about part 2, about the discretization of the ADMM also? So I'm kind of wondering, because I noticed that you use some update rule where you have this exponential negative gamma h, something like that. So I'm wondering, so I suppose this is derived based on some kind of exactly integrating part of the dynamic. So I'm kind of wondering, is it the same if we directly use, for example, explicit Euler scheme, like replacing the exponential term with just like 1 minus gamma h or something?
Yep. So I think this is illustrated here. So what is the second equation? Let me actually have it in full screen mode. So this is just the Euler integrator for the equation at the top. And the Euler integrator says that the new value of Q is always, actually this is high level, the new value of Q is equal to the previous value of Q plus the step size times the gradient, right? That's the Euler integrator. So that's exactly what's here. The new value of Q is equal to the previous value of Q plus the step size h times the gradient. And the gradient is P over M here. Okay. For this one, we did something a little bit more sophisticated. And what we did is basically, if Q was a constant in the discretization step, so imagine that this step is a constant, then you get a linear differential equation in P. So P dot is equal to minus gamma P. And so you know that the solution to that is e to the minus gamma T times P. That's exactly what this first term says. And then it's kind of, you assume that this is piecewise constant and you integrate one step. That's all what's being done. And so this is exactly the closed form solution of that integration, that the new P is equal to e to the minus gamma times the step size times P. And for the other part is just the same thing as before, Euler style. The step size times the gradient, which is this part.
I see.
Does that answer your question?
I see. So I'm kind of wondering, will the result be the same if we just use explicit Euler for the iterative equation for P as well? For example, what if we replace this exponential term with like just 1 minus gamma h?
Yeah. So basically what happens is the following, and let me answer it at a very high level. Number one, there are many discretization schemes that can be used. And each discretization scheme will give rise to potentially a different optimization method. Number two, different ones in theory could have different convergence rates. Some of them might be unstable, right? In fact, this is well known that you can have a differential equation, you discretize it, and the discrete difference equation does not converge, even though the original one could potentially have been stable. So all I've said is that this particular way of doing the discretization satisfies this property, and this is what the first theorem was, is that it's conformal symplectic, namely it shrinks the volume form. And because it does so, then you can connect the continuous and the discrete in terms of convergence rates. You could use any other discretization scheme, but then you need to analyze case by case whether the discretization faithfully follows the continuous dynamics or not.
I see. But I suppose the difference is like a higher order term in terms of h, right? But it's still kind of a significant difference. May not even be stable. So
yeah,
I see. Thank you.
Yes. So I guess what I'm simply saying here is that at least for convex functions f, this discretization preserves the stability properties and preserves the convergence rates of the continuous differential equation.
I see. Thank you very much.
Hi, Professor. So,
Yes.
yeah, sorry, sorry, this is muted. Yeah, yeah. So I want to ask a related question about the discretization. So if I still use the conformal symplectic integrator, but I swap the order of the Q and the P, right? So because in both the conformal and also the later one, the algorithm, so you in the differential equation, you show first the differential equation for Q and then P, but actually in the discretization, you actually first update the PK plus 1, then update the QK plus 1. So what if I first update the QK plus 1 based on QK and the PK, and I think that should still be just the forward or backward discretization. So that's very subtle difference, right? So what makes you choose this specific type of discretization? Does this lead to a better convergence in theoretical or empirical, or both you examined
Yes.
both type of algorithms?
Yeah, great question. So I didn't talk about it, and this is in a different paper. It's also by Guy Frank, and if you search in his Google Scholar the word splitting methods, then you will see that. So if you use forward-backward discretization, then the issues that you cannot solve for the pk plus 1 necessarily in closed form. So you get additional operators and splitting methods. And in fact, he has an entire theory of connection between splitting methods and proximal operators that also emerges the discretizations of this type of dynamical system. This is not, so going back to the basic principle, I think, when the objective function f is convex, it is the case that which ones of those discretization schemes are adequate and faithfully preserve the dynamics and have guarantees of convergence. I think this is relatively well studied. But the question of matching continuous and discrete rates is the one that was not studied and is a property of this particular discretization.
I see. Yeah, because I think that maybe the forward or backward discretization would make a very little difference here, because so it has the same high-level idea of using the decrease in volume, right? So
I guess I'll need to do the calculations. I don't see it as quickly as you do, but maybe you're right. I've not done it.
yeah, because we previously used a similar. We studied the different the forward and backward discretization method for the mirror descent algorithm. Actually, as long as both discretization are explicit, we found that the convergence actually are the same.
But do you, I mean, going back to the property that I was after, is it possible to show that this is the case?
We didn't use this kind of, yeah.
That is the property that I've been talking about all along, that it needs to be equal to this.
Yeah, I think this may be the key, I think. Thank you.
Yeah, I think that may be because the updated rule Rene is using is called leapfrog, which is a technique used for this Hamiltonian dynamics or systems. I think in order to guarantee the conformal symplectic, I think the leapfrog-based update may be essential.
Yeah. That's right.
Yeah. Okay. So we got a question in the Q&A, and so Bangsu, do you want to just unmute yourself to ask the question directly?
Oh yeah. All right.
Okay. Great. Thank you.
Thanks. Thanks for a very interesting talk. Are there any corresponding continuous, differential equation models for second order methods like Gauss-Newton or quasi-Newton methods?
I've not studied them, so I am not familiar to the point that I could tell you how, but I think the answer should be yes, in the sense that you follow the same process that I just described, which is that you just need to take the optimization method and then just take the continuous limit. So let's say you take the Newton method. Well, I will need to think about it, but I think in the case of the Newton method, right, you're going to have minus the Hessian inverse times the gradient.
Right.
And I guess the only issue is that you don't have a difference of xk plus 1 minus xk. So I don't see how you would do it immediately, but I'll need to think about it. But I don't see why not.
All right. Thank you.
In fact, now that I think of it, right, so you will have in that case, maybe I'll just go back to the gradient descent derivation to facilitate, right? The main difference is that you can write xk plus 1 is equal to, let's say, the Hessian inverse times the gradient. And so you can always write that, you can always subtract minus xk from it, and you're going to get something like the Hessian inverse, the gradient minus x. So you're probably going to get, again, something like x dot. No, maybe I shouldn't be thinking real time. Maybe let me postpone it. I didn't get it as I thought I would.
Okay. Thank you.
Thank you. Yeah, is there any other question from the audience? Okay, so let me ask one more question. So in the third part, in the last part of your talk, you mentioned that by adding some subnetworks, you can remove some spurious local minimum. So I wonder, so this idea sounds really interesting and useful. So have you implemented this kind of algorithm? I mean, it's more like an online architecture kind of technique. Have you tried implementing such kind of algorithm and see if the algorithm really can help escape from the, for example, spurious local mean or saddle point or something like that?
Yes. So let me try to illustrate it maybe with the simplest problem that you can possibly imagine. So imagine that you just have a linear network, okay? And if you have a linear network with a single hidden layer, then the training problem with a square loss is very much akin to matrix factorization, right? And so if you have matrix factorization, UV transpose, you can always decompose it as the sum of rank 1 matrices, right? And so in that particular case, adding a neuron is adding one term to the factorization. Okay, and so the rank of the factorization is equal to the number of neurons.
Right.
Okay, and so in that low rank matrix factorization, what this process is doing is, in fact, I'll illustrate it with, even though it's, let me actually be concrete. I think it wasn't there. Okay, so actually, let me do it here because it's very well connected here. So suppose I'm not doing matrix completion. So the P omega supposes the identity, right? So exactly matrix factorization, and I add that regularize. So this is exactly one of the regularizers we can consider. And so in fact, this is a regularizer of degree 2. The matrix product is a regularizer of degree 2. So the homogeneity of degree 2 applies in this particular case. How can we implement it? In fact, this is a particular case of an implementation where we could have done it in that way, in which you begin with a matrix of rank 1. So A is only a vector and B is a vector. And in that case, let's say you arrive at a local minimum, and then you decide to add a second column.
Mm-hmm.
The addition of that column is going to be exactly based on left and right eigenvectors or singular vectors of M minus AB transpose at the kernel.
I see.
In other words, I find a local minimum, A comma B. I do M minus AB transpose. And the left and right eigenvector give me the descent direction for this problem.
Right. I see. So it's like a Frank-Wolf algorithm.
Yes.
I see. I see.
And well, it depends on the case. So there are other regularizers. So another way to write the regularizer is sum of products of norms of the columns of A and B. In that case, you can do it with alternating proximal gradient style methods. And so essentially, in fact, the meta algorithm that I'm talking about is the descent. When the rank is fixed, you can use any descent method that you want. And the main addition is once you are at a local minimum, it tells you whether a descent direction exists. And if it does, you augment it and it gives you the initialization to continue now in a larger space.
I see. Right. I see. I got your point. Yeah, it's like
it also gives you the guarantee. In fact, the main result actually for matrix factorization is that it gives you the guarantee that when you have sufficiently many columns on A and B,
right,
if you add one more, that's going to be 0. So there is no descent direction.
Right. Yeah, that makes sense. It's like you try to find the right level of over parameterization to recover the underlying low-rank matrix, and this kind of idea can be carried over to linear networks, as you have done in your experiments.
What is very interesting is that everything I've said is extends to deep networks, and you can add nonlinearities, and the key of everything is that the maps need to be homogeneous.
Okay, then you have to use a Raru or leaky Raru, this kind of activation function to make it homogeneous.
But it could be a polynomial as well.
Right, yeah.
Yes.
A homogeneous polynomial.
Yes. That's right.
I see. Great. Yeah, that is a very, very interesting idea.
Chicha, I wonder if I can ask another question.
Oh, yeah, please. Yeah, I already added you to the panelists, so feel free to ask.
Thank you. Really, very interesting talk. And thank you for giving this good talk. So I have a question regarding the discretization part. So we know if we take the step size to 0, then the proximal operator, proximal step, and the gradient step are equivalent. Just like forward Euler and the backward Euler will become equivalent. But when we take discrete steps, the two gradient descent and the proximal descent are different. The proximal descent being more stable when you can't do it, right? So I wonder if you have considered extending your work of discretization from gradient to proximal.
Yes, in fact, we have one entire paper on splitting methods in continuous and discrete time. And the idea there is that you take a continuous differential equation, like x dot equals to some flow. You divide the flow as the sum, you split the flow as the sum of, let's say, 2 flows or 3 flows, depending whether it's 2-way splitting or 3-way. And then you follow the flow of one for, say, half time, and then the flow of the other. And with that, you can generate all splitting methods. I think you've contributed greatly to the discrete time splitting operators. And so we have a paper with the analysis of those in the continuous time as well. But I don't have any slides here, so it'll be very hard to comment further, but happy to discuss that in more detail offline.
Right, that sounds very interesting. I'll look up for this paper.
I'll send you the paper right after the talk. Yeah.
All right, thanks.
Thank you. Thank you for asking so many questions. And if there's no more questions, so we will wrap up here. And let's thank Rene again for his great talk.
And if you have any other questions, please do follow up with him. Thank you, Rene. Thank you.
Thank you.